Good morning, everyone. Please take your seats. I'm Dr. Clifford Bobb. I'm a professor of political science here at Duquesne, and I wanted to welcome you to our first breakout session of the conference. I think it's really going to be an interesting session, a great follow-up to the really inspiring and fascinating talk we just had from Dr. Brinkman. We have two papers that we're going to present today. Each of our speakers will speak about 20-25 minutes, leaving us with some time at the end for questions for both of them. So let me first introduce Dr. John Stolz, who is a professor here at Duquesne at the Bayer School, professor of environmental microbiology. He's also the director for environmental research and education. He has a PhD in biology from Boston University. And he's going to speak to us today about climate change and the Gaia hypothesis. John.
Thank you so much. And again, if I say it's a pleasure to be here, I just walked over from my office. But this is really exciting, and I'm so glad that the university has been able to put this together. And to me, for my talk, it really brought back a lot of memories, and you're going to see why. But I had the wonderful opportunity to work with Lynn Margulis as a graduate student, and it was serendipity. I mean, I applied to BU because my sister lived in Boston, and I needed a place to go to graduate school, and they never sent me the list of faculty. So when I got there, they said, well, you have to meet this person, and it was Lynn. And we got to talking everything, and she actually, at that point, I said I wanted to study life on other planets. And she said, well, you really can't do that, but this is what we can do here. And why that was so important, because at that time she had been collaborating with who basically the father of the Gaia hypothesis is, and that's Jim Lovelock. And it was really exciting for me because the first thing she did was she sent me out to NASA Ames to attend the second post-Viking meeting, which again, it was about, back in the 70s we had sent probes to Mars to look for life and came back empty. At least that's what they thought. Well, fast forward, well, don't you know, just earlier this week there was that announcement from NASA that they found not only water, but they also found perchlorate. And why that's important is because in my neck of the woods, perchlorate is a food source. So the thing that Jim had done way back when, back in the 60s, so back there, Lovelock first published the idea of the presence of life could be detected by looking at atmospheric composition back in 1965. And he wasn't very popular with NASA because you don't have to spend that money. You don't have to do the Viking. And they're like, no, we have to go to Mars to look for life. And it more or less coalesced in this idea that it was later proposed for Mars in an Icarus paper by Hitchcock and Lovelock. Because Lovelock has this amazing history. He's trained as a chemist, but he is also recognized as the father of cryogenics. He figured out how to freeze things and have them survive, especially blood. It was a very important discovery during World War II. The other important thing was that he invented this device called that allowed you to detect very small quantities of gas. And one of the gases that he discovered or was able to detect were chlorofluorocarbons. It's kind of hard to say. But anyway, the significance of that was he realized that our use of these CFCs, if you will, for everything from aerosol cans to refrigerants, was having an impact on the atmospheric composition. And I hope we all know that we realized that they were ozone-eating chemicals. And if it wasn't for Jim's discovery, we never would have known that, and we'd probably still have a growing ozone hole today. Okay? But more important than why he came up with this idea, when he hooked up with my boss, Lynn Margulis, she was this microbiologist that was looking, again, what kind of life could be on other planets. She was working with NASA. So also, what was life on Earth billions of years ago? Because this is something that many of us don't realize, that the Earth was very different 3 billion years ago. There was no oxygen. What we're breathing right now, if we went in a spaceship and went back, we would have to wear a spacesuit because we couldn't survive on Earth. And the reason that our planet is the way it is today, or at least this is the concept of the Gaia hypothesis, is not only because of the evolution of the sun, not only because of the evolution of the Earth as a planet, but because life exists on this planet. And as a result, affects the composition of the atmosphere, oceans, and sediments. And what I will talk a little bit about today is taking it even a step further, in that it helps to not create climate, but to help regulate and modulate it. And so these are just some of the popular books that he published. But in 1979, he basically, well, back to 1974, the Gaia Hypothesis first appeared in the 1974 article in Tellus by Lovelock and Margulis. So basically, Lovelock was saying, if you look at our atmospheric composition today, it's 20% oxygen, but you can detect significant levels of methane. You can detect significant levels of ammonia and other reduced gases, which should not exist in the presence of oxygen. And where did that oxygen come from in the first place? It came from life. These unique little, the first real polluters of the world were these organisms called cyanobacteria, who figured out how to cleave water to fix carbon and harness sunlight. And as a result, they produced oxygen as a byproduct. And of course, there were a lot of organisms that probably first major mass extinction, because back then, I told you, there was no oxygen. So a lot of organisms that were alive back then didn't use oxygen. And we figured those organisms up on Mars, if they do exist, probably are not using oxygen. But the whole idea is that by looking at the atmospheric composition of the Earth, an alien intelligent life form would be able to say, you know what, there's something weird going on there, and we call it life. So, put it distinctly, the Earth is a cybernetic system where the biota, or all living things, interacts with the atmosphere, hydrosphere, and lithosphere, meaning the air we breathe, the land we stand on, the crust, and the watery part of the planet, the oceans, etc. They interact to maintain the long-term habitability of the planet in the face of perturbations. This was another really interesting innovation or discovery, enlightenment, whatever you want to call it, epiphany of Earth scientists back in the 60s. Before the space program, no one had ever looked back at the Earth as a planet. But when you see that picture from the Apollo mission where they show Earthrise on the moon, it's astounding. And I got a chance to meet Rusty Schweikert, who had an epiphany because he was circling, I believe it was a Gemini mission, and he was out on a tether doing a spacewalk, and the camera got jammed, and his co-pilot said, could you wait a minute, let me see if I can fix this out. And he's looking at the Earth going, this is amazing. All this stuff exists, and we have this small shell of an atmosphere. And that's part of this whole biosphere. But anyway, if you strip away all life on Earth, you find out that we, just like the moon, have had major impacts from comets and other things. That we've got this thing called tectonism, violent volcanoes, moving continents. And of course, a biologic perturbation was oxygen. So life persists because we've been able to adapt to those things. So initially, he proposed it as a homeostatic system, like you have in your home, a furnace, okay? And your air conditioner. If you set your thermostat at 72, when it heats up in the summer, what happens? The AC goes on, cools things down. When it gets cold in the winter, what happens? The furnace goes on, warms things up. Okay, that's a cybernetic system. That's a negative feedback. Okay, but then he realized that indeed this set point, if you will, the 72 degrees, actually moves. So way back when, we had an atmosphere that had no oxygen and a lot more carbon dioxide. I will tell you, there was way more, or at least the geologists tell us, there was way more CO2 in the atmosphere back then. But one of the remarkable things about life and what it's been doing over 3.5 billion years is removing that carbon dioxide. Because another weird thing is that the sun has actually been heating up as well. And so that balance has actually compensated for the increased solar luminosity. So again, the point is that he recognized that the global climate system set point could change, and indeed has. More importantly, as for what we have to deal with, that life was not a passive passenger on this planet, that we had a crucial role in maintaining the habitability of the biosphere. So we have this wonderful thing, this planet that has a life support system, okay, that allows life to persist. It's persisted over 3.5 billion years. People talk about the dinosaurs lasting over 200 million years. And how many millions of years have we been around? Hopefully, we'll be around for longer. But anyway, so what are some examples of this Gyan hypothesis, or the idea that life has a role in climate? Things like autotrophy, carbon fixation, the process by which living organisms, plants, photosynthetic bacteria, and other what we call chemoautotrophic organisms are able to suck CO2 from the atmosphere in their environment and make carbon, organic stuff that, again, ultimately we eat, biogenic carbonate precipitation, microbes and shell-forming organisms, another sink for carbon dioxide. Okay? So it turns out that over life's history, various mechanisms of removing that carbon dioxide that was on the early Earth, because we were very similar to Mars and Venus, having much more CO2 back then, but life itself has been responsible for removing a lot of that carbon dioxide. But even more, and maybe this is one of those challenges, more recently, once we started thinking in these terms that life has a role, well, what other things could they do to help modulate climate or various things like atmospheric composition, et cetera? The discovery that phytoplankton release dimethyl sulfide, which leads to cloud formation, which can change the reflectivity or how much sunlight actually bounces off the surface of the planet. So dimethyl sulfide production by phytoplankton is involved in cloud formation, and albedo, which is that reflectivity. And lastly, we like to think of rainforests not as sources of diversity, but rather the sweat glands of the planet. In that, much like when we start to heat up, we sweat, and that sweat evaporating cools us off, plants do the same thing in the rainforest. So when you look at rainforests very carefully, you see that where are the clouds? The clouds are over the trees. Why? Because the trees are sweating. Okay. So again, this idea was revolutionary at the time, back in the 60s, early 70s. NASA did still go ahead with sending the probes to Mars, even though the Martian atmosphere is in equilibrium, if you will, and there's no little green men running around. But they said, well, wait a minute, this is a hypothesis. It'll never be a theory because you can't test it. We don't have another planet to do this with. Okay, you don't have a control planet. So he came up with this idea called Daisy World. And Daisy World is just a simple way in which this amazing thing we call biotic potential, or the ability for any individual species, given enough food and resources, could colonize the world. Okay? If we wanted to do some of the math, I could tell you that a single bacterium that doubles every 20 minutes within 48 hours will be a mass several times the weight of the Earth. It's that bizarre, but that's how quickly things can grow. Nevertheless, his concept here of Daisy World was white daisies and black daisies. Okay? And the stressor, because again, a lot of these things happen when you have a stressor. Okay? Why do you need to be able to rebound? Why do you need to be able to adapt? Well, because stuff happens. Okay? Whether it's a massive comet coming in and slamming into the oceans, or in this case, just the normal development of our sun. It was much cooler back then. But the cool thing was we had more carbon dioxide, so the planet was warmer. So in the face of increasing solar luminosity, how do you adapt for that temperature? Well, it turns out, just with a simple model, black daisies absorb more heat, technically in Daisy World, so they grow better at cooler temperatures. White daisies reflect more light, and this is known as the albedo effect, and they would grow better at warmer temperatures. And so if you look at the populations, initially you get most of the planets covered by black daisies, and eventually they kind of peter out because it's starting to warm up. The white daisies are, again, in the background for the most part, but then as things start to warm up, they actually start growing more and cover the surface of the planet. And so you get first a lot of black daisies, then they peter out. First you start with a few white daisies, and then they kind of populate the surface. And a very strange thing happens, is that for a very long period of time, or over a long increase in this warming sun, what happens to the temperature at the surface? It stays pretty constant. But here's the other cautionary tale, is at some point, well, you've covered the world in daisies and white daisies, and there's no more place to go, and eventually it gets too hot, and boom, there goes the planet. So there's, it's a simple model, but it just gives the principle that how biological systems can adapt and help modulate. As I said, they don't create, but they modulate the climate. Okay, now, here's our new stressor. So in my mind, in the Gaian view, okay, the carbon dioxide increase is the experiment. We are the living experiment for Gaia. And if Gaia works, we're okay. If it's a myth, we're in real trouble. But anyway, here's the fun part. Okay, Stolz starts graduate school. Okay, 1977. The most amazing thing, and this is what blows my mind, I debated a Federalist in the spring, a climate change denier, and I said, I'm sorry, I started graduate school in 77. We're up to now 400 ppm. It was at 330 back then. So in my academic career, it's gone up 70 parts per million. And how many billions of years did it take to get down to where it was prior to the Industrial Revolution? 3 billion. Actually, 3.5 billion. So we're flipping the switch in a very short period of time, a nanosecond in celestial time. Okay? But interestingly enough, because I was Lynn Margulis' student, what was she talking about that back then? People talk about that these climate scientists, all they care about is their grant money, and that's why they're making such a to-do about this. No, we were talking about global climate change back in the 70s. People like Jim Hansen, okay? People like Stephen Snyder. Why? Because that Mauna Loa data, this is basically the carbon dioxide levels in the atmosphere above Mauna Loa in Hawaii. It's another thing. Oh, yeah, everybody wants to go to Hawaii, right? No, it was a good place to do this. But I don't want to say this is proof of Gaia, but if you look closely, there's this oscillation, and it's an annual oscillation. Why is that? The Earth is breathing, okay? This is winter. This is summer. Turns out that most of the landmass is in the northern hemisphere, so most of the forest is in the northern hemisphere. So what's happening here? During the winter, no photosynthesis or no appreciable plant photosynthesis, and we're burning fossil fuels to keep warm, so CO2 levels go up. During the summer, well, yeah, we still have to burn some fossil fuels for the air conditioning, but a lot more primary productivity, a lot more photosynthesis, a lot more carbon dioxide natural sequestration. So this is the planet breathing, okay? This is life. This would not happen if there was not life on the planet. So that's really reassuring that Gaia can have, or life on Earth can have, a very important thing. But this is the scary part here. Okay. So you heard last night a little bit about what the scientists believe how climate change or how climate regulation occurs. And principally, it's a geologic process that occurs over hundreds of millions of years called the Carbonatesilicates Cycle. Simply saying that when things warm up, you get more evaporation, you get more rain, more precipitation, more erosion. The erosion goes into the oceans, providing more nutrients and other things for the shell-forming organisms and phototrophs in the ocean, sucking down that carbon dioxide. The carbon dioxide levels go down, having a cooling effect. Okay? So, and this, of course, has been further attenuated by the fact of plant life and animal life that form shells. So it turns out that this cycle was a little iffy, if you will, early on. But as life developed and became more abundant around the Earth, it was better regulated. So now we know how things go as far as with glacial and interglacial periods and how the biota responds to that. But this, and of course, this is a really busy sign. Okay, I realize that, and I apologize, but we get really excited about it. And what I want to say is that, okay, so life has been on the planet 3.5 billion years. Modern climate scientists talk about plant life and animal life having a very important role, especially shell-forming organisms, clams, forams, corals, okay? And everybody's worried about the corals going away because they're a major sink for carbon dioxide. And the idea is that, with ocean acidification, it's really going to screw things up. Well, it is going to screw things up, but they helped out in the past, and they will help out in the future. What the work that my colleagues and I have done over the last few years has been working on this idea that these microbes that populate this Earth are actually, or stromatolites, and I'll tell you exactly what they are in a second here, and microbial mats are bioreactors. That is to say that they are very important in cycling important nutrients that we need to survive. But more importantly, that down here you can see that there's coupled cycles of carbon, oxygen, and sulfur. So there are bacteria that make this oxygen. There are bacteria that eat that oxygen or use that oxygen in their respiration. And they, again, are regulating or help modulate carbon dioxide in the environment. More importantly, and if you were the chemist, you get all excited about this, but the take-home story here is that there are a number of different mechanisms in which large amounts of carbon dioxide can be sequestered in certain microbial systems. So one of these, they're called stromatolites, and basically the microorganisms have their time as their period of dinosaur about being big. No, bacteria have always been really small, but the thing is they made these structures. This is a geologist for size. This is a structure we call a stromatolite. It basically is a bunch of carbonate rock that has been deposited by the activity of microorganisms in a near-shore marine environment. Okay? What were they doing? Sucking down carbon dioxide. Okay? So the thing is, they not only provide us with evidence for life back 3.5 billion years, because this is the kind of living mode that these microbes had, but they produce significant carbon deposits and organic deposition. Fast forward to today, and my students are jealous of me because I get to go to places like Shark Bay, Australia, and little islands in the Bahamas. But even today, these processes are going on. They're ignored because everybody wants to go swim in the Great Barrier Reef. I'm on the other side of the country looking at these things. These are really more important. But anyway, and I don't want to use up too much time, and I'm almost done. The important thing is that when you're able to couple certain biological processes, certain microbial processes, you can produce and sequester huge quantities of carbon dioxide in the form of both. This is inorganic carbonate, and this is organic carbon. We've got a lake in Bermuda, another nice place to visit, called Mangrove Lake. In 4,000 years, they have the microbes there have produced over 11 meters of organic matter like this. But that's 4,000 years. Okay? So again, we can see that what's the microbial contribution to CO2 regulation? Well, basically, cutting to the chase here, in the sake of time, the microbial respiration and carbon sequestration appears to have contributed to climate regulation in the past. Okay, because they're able to do things when it gets too cold, they release carbon dioxide, more respiration. When it gets too warm, they start sequestering less respiration, but more carbon burial, more CO2. But the interesting thing is, okay, so more importantly, these processes may not be sensitive to lower pH. We've got some papers coming out with my colleagues do, saying that these microbial systems are not that sensitive to pH. However, the conditions that they live best in would promote the greatest carbon sequestration, have an extreme negative impact on aerobic aquatic life, and it would be us. So in other words, my point is that there are these microbes that don't use oxygen because they go back way back when. Okay? But they will eventually, I don't want to say save the planet. But just to conclude, there has been a rapid increase in carbon dioxide from 330 ppm to 400 ppm in just the last 30 years, my academic career. Okay? That's scary. While living systems can modulate oscillations in the climate system, which again is the idea of the Gyan Hypothesis, there is a limit to what they can do. Okay? On biologically based carbon sequestration via both carbonate and organic carbon burial can remove significant quantities of CO2, as it has in the past. But we're talking about geologic time frame. We don't have the time. We're not going to be around. And more importantly, I would say that what Gaia tells us, or this idea that we're dealing with a global system where different pathways and different cycles are interconnected, any anthropogenic solution, whether it's seeding the oceans with iron or other things, must recognize these linkages and possible feedback responses of the global climate system in order to minimize unintended consequences. I have colleagues who say that if you were to seed the ocean to stimulate photosynthesis, the net result would actually be more respiration and, at the end of the day, more CO2 actually being released. So again, if we don't at least take a Gaian view of this climate system, we run the risk of focusing on a particular aspect and having a bad outcome. But anyway, thank you very much. And no time for questions?
I thought we had questions jointly at the end.
Okay, that's a great idea.
Thanks very much, John, and very interesting presentation, ending kind of on a cautionary note about what our public policies might do in a Gaian worldview of impacts on the climate through public policy, potentially. But now we move on to another great speaker, Dr. Neil Donahue, who is a professor of chemical engineering, chemistry, and engineering and public policy at Carnegie Mellon University, just down the street from us. He's also director of the Steinbrenner Institute of Environmental Education and Research, and he's a science and engineering ambassador of the National Academies of Science and Engineering. He has a PhD from MIT, and he will speak to us today on the topic, how climate change and air quality are interconnected in the developing world.
Thank you. I think that, no, it's just attached. I have a tendency to move around, but I'll do my best to stand still here. So, as I get set up, just for a little personal note here, in fact, I might even be able to blank the screen. Nah. So, Control-L, yay. My father, as it happens, received his PhD from Rockhurst College in Kansas City, so he was educated, not his PhD, I'm sorry, his bachelor's from Rockhurst College in Kansas City from the Jesuits, so it's nice to be here at Duquesne, not quite the same society, but close enough. And was a physicist initially at the University of Pittsburgh, so I was born in Pittsburgh and spent my early years here. And he is, in fact, the person who discovered that Venus had an ocean, and that ocean eventually went away as the Earth as the sun got somewhat brighter about 4 billion years ago during the what was the dim young sun and is no longer the dim young sun, and experienced what we call a runaway greenhouse effect. So I have a certain personal history, invested interest in some of this science. So this figure here is a figure of the global average surface temperature for the last 130 years or so. It's the tiny little bit at the end of the temperature record that Richard Alley showed last night, if you were here last night. And you see the temperature. I've switched it to degrees Fahrenheit, and it's the average from roughly the global average surface temperature at 1900. So it's a change since then. And you see it's gotten about a degree Fahrenheit warmer or so since 1900 in the past century and change. And the temperature is going up and down, but there's an obvious trend upward. And now on that, I'm going to put a red curve. And that red curve is a model that represents that global average temperature, or reproduces that global average temperature. It's what we call an empirical model as scientists. But it's got 4 simple contributions that I'm going to describe to you. And this is a little bit of what Richard was saying about we understand this science extremely well. And there are predictive elements here that are useful as well. But you see that red curve now. And you'll actually notice that the temperature record, I cut it off at 1997. And that's kind of important. And I've trained this model, in the jargon of our trade, on those data from 1890 to 1997. And then you see the red model continuing happily onward until about a year and a half ago when the particular data record ended out. And it's got some ups and downs to it, as you see. But that is a prediction based on these empirical measurable attributes that I'll tell you about in a little bit. Then you see there's a big spike and then sort of up and down a bit. So that's the prediction. Now, if I take the actual observations for that last 15 years and I overlay them, you'll see the prediction isn't too bad. And in fact, if you look at it carefully, you'll notice that the prediction was a little bit low. Turns out it was a little bit warmer over the past 15 years than we otherwise thought it would be. That's really important, and we'll get back to that. It was a little bit warmer over the past 15 years than this prediction would have predicted. Okay, the 4 contributions to this are pretty simple. The first thing is every now and then a volcano goes bang. And not just bang like a regular old happy volcano that wouldn't be so happy if you were right next to it, but really kablooey. And it's kablooey enough to put a significant amount of material, sulfur dioxide, into the stratosphere and put a layer of haze around the planet. And the last one that did that successfully was Mount Pinatubo in the Philippines. This is a catastrophe, by the way, for the people nearby. Right? I shouldn't make light of it. Pinatubo was a big deal. A lot of people died. So with the really big volcanoes, Krakatoa is probably the most famous to people. Mount Tambora in Indonesia in 1815 generated what was called the year without a summer. So when this happens, the Earth gets colder. So I've shown this record from black down to green is the influence of that on temperature according to this empirical model. So in 1992, when Pinatubo erupted, there were a couple of years subsequent to that when it was, in fact, quite a significant amount colder than it would otherwise have been. So we have a cooling effect. The second contribution is the sun itself. In addition to having gotten slightly brighter over the past 4.5 billion years, it gets a little bit brighter and a little bit dimmer and a little bit brighter every 11 years. It's called the solar cycle or the sunspot cycle. Oddly enough, when the sunspots are out, when the sun has acne, it's a little bit brighter and a little bit warmer, and we are a little bit warmer when sunspots are at their maximum, and at solar minimum, the sun's a little bit dimmer, so there's a little bit less solar heating on the Earth, and it's a little bit cooler, and we understand that solar effect. And so now I've added on the yellow bit for a bright yellow sun, and Mr. Golden Sun is doing a little bit to change the surface temperature of the Earth, and we can see that. And so now that green curve represents those 2 contributions. I've only got 4. The third contribution, and those first 2 contributions are genuine influences on the heat budget, how much heat is coming into the planet, either because the sun is giving us more or less, or because this little haze layer in the stratosphere is bouncing some light back into space. So it directly affects the heat budget. The third influence on the atmospheric temperature has to do with where we put the heat, and that influence is El Nino. Because what El Nino is to a meteorologist, during an El Nino year, the winds, the trade winds in the equatorial Pacific are calmer, are less than they normally are. And because of that, there's less wind driving the ocean circulation in the Pacific Ocean, and that wind driving the ocean circulation is one of the contributions to driving the overturning of ocean water. And because of that, during an El Nino year, there's less heat being taken up into the deep ocean and the atmosphere is warmer. So El Ninos are years when the atmosphere is warmer, and the ocean, if we could measure its whole temperature, would be correspondingly a little bit cooler. Same amount of energy coming into the planet, we're just putting it in a different place. And so during El Nino years, there are big spikes in temperature. It's warm. And you can see in 1998, there's a large upward spike in the global average surface temperature. That's a year that certain people use conveniently as an anchor point when they're looking at global average surface temperature to make arguments, pedantic arguments. All right, that is 3 of the 4 terms in this conversation, and you probably already know what the 4th one is. The 4th one is us. So if we add in the climate effects of human activity, mostly carbon dioxide, but I'll break those down, but mostly carbon dioxide, then we get the 4 contributions to that curve, which you'll remember very nicely reproduced the observations over the past 150 years. And I can take now that just the contribution from carbon dioxide and other greenhouse forcings and overlay that on the reproduction. And you see that it explains the general upward trend because the other 3 contributions didn't do anything over time. There was no secular trend. It was just bouncing up and down. The entire reason for the significant increase in temperature over the past 150 years, 250 years, is us. Again, as we heard last night, that is not under debate. That's what's causing that. So now what I want to do is break down a little bit those contributions to this magenta human forcing term. So that's the overall. Now we'll talk about what we call climate forcing. So that was the effect on temperature, and now we're looking here on the y-axis of this graph is how much heat is actually, extra heat is coming into the system, and we measure it in watts, right? That's power, energy per second, joules per second, per square meter of surface area of the Earth. And it's not a huge number, a couple of watts per square centimeter of the Earth, but it has a huge effect. And this is the overall climate forcing, the best estimate for overall climate forcing from the Intergovernmental Panel on Climate Change over the past 130 years. Okay? So an upward increasing climate forcing until about 1950, 1960, and then a dramatic increase after that is the essential bit. So now let's break down these contributions, and the first contribution is a cooling term from human activity. And as you'll see in a little bit, this is actually a significant part of what I study. And this is the cooling term associated with the claw hypothesis that we just heard about, and we'll talk about it more. Actually, this first cooling term is direct scattering. It's more like the volcanic term, but aerosols in the lower atmosphere mostly that just bounce light back into space. The second contribution is also a cooling term. This is the indirect effect in which particles influence cloud brightness or albedo, and that is what is part of what's behind the claw hypothesis, which I will talk about a little bit more. So I've started with the human influences on climate, and I've given you two contributions that are making it colder. And we'll talk about those significantly more in a little bit. Now let's add on some of the warming terms. The biggest warming, right, forgot about this slide. So the two things that are making us colder have to do with particles. Particles bouncing light, scattering light, as you see in the left there. This is a photograph of Beijing on a not-so-good day in January, and on what's called a blue sky day on a nice day. And I've been in Beijing on a nice day and a bad day. And actually, there's mountains in the background that you can't see. So even the blue sky days in Beijing aren't so terribly blue. So the issue with these particles that do cause cooling, that bounce light back into space and also change cloud properties, is they kill about 3 million people a year around the planet. So they are actually a public health catastrophe that we'll talk about more. Now let's look at the warming terms. So we'll start with carbon dioxide. It is by far the largest contribution to this whole story. And this is fossil carbon dioxide associated with producing energy. It is coal, it is oil, it is natural gas, and it's a big deal, and it is essentially the whole story. It isn't obviously the whole story. I'm a scientist, and I'm talking to you about the subtleties in here. But the big part of the game, the big part of the story is fossil carbon dioxide, and that's why Richard Alley spoke so much about energy last night. That's why I'll talk about it more. You can't deal with this problem, you can't address this problem without addressing fossil carbon dioxide and the energy system of the planet. There are other warming contributions. This next reddish curve block is the contribution from methane. Methane itself is a greenhouse gas, as most people in western Pennsylvania and the Marcellus Shale area know. Strongly absorbs infrared radiation, so it also contributes to global warming in the time that it's on the planet. It's about 15-20% compared to the carbon dioxide contribution. The next is nitrous oxide, the green revolution. When we fertilize fields, there is some emissions of N2O. N2O is a very long-lived greenhouse gas, and yet again, it does contribute a little bit to global warming. The next are the chlorofluorocarbons, whose concentrations have increased from nothing to the present day. They're extremely long-lived. They were discovered by Jim Lovelock when he developed the electron capture detector. And in fact, my PhD advisor, Ron Prinn, collaborated very closely with Jim to measure these things back in the 70s, and they continued to measure them to this day, to determine what the sinks of chlorofluorocarbons were to make sure or to test whether the CFCs were actually getting into the stratosphere. And I've worked on that problem a great deal over many, many years, but we won't talk about it now here. The CFCs, in addition to destroying ozone, are extremely strong greenhouse gases, and we've shown them there. And then finally, the last contribution here is from extra ozone in the lower atmosphere. We like ozone up in the stratosphere where it protects us from ultraviolet radiation. Down here, it's an oxidant. It greatly enhances the risk of asthma. It's a regulated pollutant in the National Ambient Air Quality Standards, and it's also a greenhouse gas. And so the increases in ozone have also led to warming, and a rather significant amount at that. So those are the various contributions to what we call the anthropogenic forcing on climate. The aerosols, in addition to having this cooling effect, and in addition to killing a great deal of people, represent by far the largest uncertainty in our understanding of the picture that I just gave you. Because there is uncertainty, we work on this uncertainty an enormous amount, and it's essentially what drives our field, is to understand these things more. And another thing that Richard Alley pointed out last night is that, in general, our uncertainties are somewhat skewed. And so let me walk you through this figure a little bit more than just tossing it up here. So we'd have this total forcing since the dawn of the Industrial Revolution on the x-axis, and then you see a bunch of gray curves. And you see a horizontal colored bar across the top. That's the distribution that I just showed you from the various contributions, and the colors are the same. So the red carbon dioxide, the dark magenta methane, the purple nitrous oxide and chlorofluorocarbons, and the ozone. And you add them all up, and you get the red peaked Gaussian distribution there on the right-hand side. They contribute a lot of warming, and it's a sharp distribution, which means that, and this is a probability distribution, our best estimate of that is, we don't know it exactly, but we know it quite well. So within 10% or so, 10 or 15%. So it's very unlikely to fall outside of that range, very near the peak. We understand it well. And then on the left are the two gray bits, which are the aerosol contributions to cooling. And we don't understand them well. And so our best estimate for the distribution is extremely broad. There might be -3 watts of cooling associated with the aerosols. There might be even a little bit of warming, net warming associated with the aerosols. So we don't understand that well. And that is a problem for climate policy for the following reason. The observations that I showed you are warming. We know it's getting warmer. What we don't know is what we call the climate sensitivity. How hard have we pushed the system to make it that much warmer? And if the aerosol effect on climate has been, another thing I should say, the climate effects have to do with a change. What we really don't know well at all is what the aerosols were doing in 1750. And it's exceptionally hard to figure that out. So that's the issue that we're dealing with. So how much has this aerosol cooling changed from 1750 until now? There were always clouds. There was always white clouds scattering light back into space. How much has that changed? There were always aerosols scattering some light back into space, though not so much before the Industrial Revolution. How much has that changed? It might have been a lot. We may have added a lot of cooling to the system, in which case the forcing from aerosols is way over on the left. And if that's so, then we haven't pushed the system very hard from 1750 to now. And yet it has gotten a lot warmer. So that would mean that the climate is very sensitive to that forcing. And that's bad, because that means if we force it more, it will get much warmer. And we have to be even that much more urgent in our action. If, however, the aerosol effect has been closer to zero, that means we have pushed the system relatively hard. And if we have done so, it has gotten warmer. Again, as Richard said last night, there's very little room to go toward the super happy story. Right? It is going to get warmer. It has gotten warmer. But it would mean that the climate system is somewhat less sensitive to that forcing, and that gives us a little more breathing room to develop policy. And if we're going to try to reach a temperature goal, then we have to know what the temperature is going to do if we exert a certain amount of forcing. So I'm going to show you just a little bit, and I have to zip through these slides because of the constraints of time, but I'm an academic and we like to talk a little bit about what we actually do. And one of the things I actually do is particle physics at CERN, and this is literally true. We have an experiment going on right now, but the particles we're interested in are atmospheric particles, not Higgs bosons, and we actually live on you can't really see this very well here, but this is the CERN campus. There's the Geneva airport over there to the right. The international border is roughly that dashed line there, so that's Switzerland to the right and France to the left. It goes right smack through the middle of CERN. But in the middle of the CERN campus is a little accelerator, it's not that little, called the proton synchrotron, which was the physics experiment of the 60s. And then this ring that you can just see here, you can't actually see it on the ground, but it's drawn here in this photograph, is the accelerator that was used during the 80s and early 90s. And then the big ring is the Large Hadron Collider where they look for Higgs bosons. And in order to get protons on the big ring, you don't just start them up from zero. You got to warm them up. So we in the proton synchrotron are in the hole. And then this ring is on deck, and then this is finally in the big ring. So whenever the LHC is on, we are too. And we use those protons, we actually use what are called pions from the proton synchrotron as mimics for galactic cosmic rays, which generate ions in the atmosphere and can help stabilize particles. And it's also a way of testing some of those effects of the sun on climate, because as the sun gets brighter and dimmer, also the amount of cosmic rays that hit the atmosphere change. And so we're interested in how that influences particles. And we have this wonderful experiment we call CLOUD. It actually is a cloud chamber, and of course we're interested in the physics that influence clouds. As I say, we started an experiment on Monday doing one of these campaigns. And I'm just going to show you a little data, but the question here is there are two ways you get particles in the atmosphere. One of which is you burn stuff and you emit particles directly. We call them primary particles. They're the chunky stuff that comes out of diesel engines, wood smoke from forest fires. You get some particles from sea spray, which isn't our bailiwick. But the other way that you can make particles in the atmosphere is actually form them, often with sulfuric acid as part of the story. Again, that's what's behind the claw hypothesis. And that's what we're interested in. What's the chemistry and physics that actually nucleates particles in the atmosphere? So we use cool mass spectrometers. This is a mass spectrum or part of one. It doesn't really matter, so I won't explain it in enormous detail, but we can weigh charged molecular fragments in atomic mass units here on the x-axis. And we can do it with enough precision that we can actually measure fractions of an atomic mass unit, what we call the exact mass. And all you need to know is that helps us identify the molecules. And this red bit here is a charged bisulfite anion. In other words, sulfuric acid that's lost a proton. It's got a negative charge, and we can measure it with this mass spectrometer. And again, that's what's behind the oxidation. When dimethyl sulfide is oxidized in the ocean atmosphere, you get some sulfuric acid. And the sulfuric acid, in turn, is what causes the particles to form, or is part of that formation. And so here's a happy sulfuric acid or bisulfate anion. And then what we observe over time in these experiments, we can literally watch the particles grow one molecule at a time, which I think is pretty darn cool. And so we can see that become a bisulfite anion that has another sulfuric acid attached to it. And in this particular experiment, we had sulfuric acid and a base called dimethylamine in the chamber at the same time. And they like to do acid-base chemistry in the gas phase. And so now we'll have a cluster of 3 sulfuric acids, the red bit down there, but now it starts to grab a couple of dimethylamines and get neutralized. And again, you don't have to worry about the details of that chemistry and physics, but we can watch this. So this is a cluster with 3 sulfuric acids and 2 dimethylamines. And it grows. So we go from there to there to there to there, and we can watch it grow up. And so this is the process of the nucleation and formation of those particles. What I'm actually interested in is the chemistry of organic compounds in the atmosphere, which make highly oxidized products that can make clusters in sulfuric acid. And suffice it to say that we do similar experiments with that, and we can also watch those grow. They're much more complicated than the image I just showed you, because the chemistry is more complicated and fun. But we're looking at, piece by piece, how the chemistry that goes on in the atmosphere leads to the formation of these particles, which is one of the huge contributions to the uncertainty that I showed you earlier. And we won't worry about that, the rest of that. We're working on those things because we want to understand the chemistry and physics, partly because it's where fundamental science is fun, but it's also a significant part of our uncertainty in climate. Okay, these next slides are really important. So whether or not I get through my whole deck is kind of irrelevant. This figure shows an estimate for the total burden of carbon dioxide in the atmosphere. It's not the total burden, but these are the emissions. And I'm weighing it by the carbon, because the oxygen comes from the oxygen in the atmosphere. That's the poop of the early living organisms, as we just heard. The carbon is the fossil carbon. And so right now, this is historical here. The bit that looks like actual wiggly data is historical. And we're emitting about 9 billion tons of carbon, about 30 billion tons of carbon dioxide per year into the atmosphere on the planet. And then the happy straight line, it's not so happy, but it's a projection based on sort of continuing business as usual acceleration in the emissions of carbon dioxide. And there is plenty of fossil carbon available. There's going to be no trouble by 2150 getting to 40 billion tons of carbon emissions per year. We know where it is. And I can talk about the reservoirs and where they might come if there's interest later. But that's a business as usual scenario, and it's quite plausible. Okay, people may already be alarmed, but it is alarming. Now here's another scenario. Looks totally different. In this scenario, we stop where we are now, 9 billion tons a year. And instinctively, this is good. This is how we think about pollution. If I have a pollution problem, and the situation is, not great, but it's tolerable, then the instinct and the history of environmental policy is to say, okay, let's try to stop things where they are now and keep the emissions the same now. This is true for emitting sulfur dioxide, which turns into sulfuric acid and generates particles. If we keep the sulfur dioxide emissions where they are now, then we would have about the same level of sulfuric acid and sulfate aerosols and everything else that we have now within a week. That may not solve a problem, but it at least holds it steady. And then we can worry about reducing levels. And it's easy to think about carbon dioxide in the same way. So those two look really different as scenarios. Now let me give you another scenario. This is one where the total emissions around the globe of carbon dioxide go down by 2% per year. On the one hand, that's just 2 measly percent per year. Things change globally all the time by more than 2% per year. On the other hand, if you talk to anyone serious about energy policy, this is amazingly drastic. But 2% per year, going down to nothing, essentially, by the middle of the next century. And then a fourth scenario, just for fun, let's pretend that we turn it off completely right now. It's not going to happen, but as a scientist, you like to see what the story is. Okay? Now we're going to look at the projected concentrations, the projected burden of carbon dioxide in the atmosphere as a consequence of those 4 scenarios. The red one, business as usual. The magenta, freeze it now. The green, decrease by 2% per year. And then the crazy blue one where we imagine that we just shut it off totally. And we're going to start with the same the same Keeling curve of carbon dioxide emissions, carbon dioxide observations at Mauna Loa that we just saw from 1957, the International Geophysical Year, to the present day, going up to 400 parts per million. You will notice with some alarm the size of the y-axis here, and we're going out to 2150. Okay? So the business as usual scenario will do this. This is an ocean uptake model. This is what the carbon dioxide will do. By 2100, we're going to be over 750 parts per million concentration in the atmosphere. If we freeze carbon dioxide at current levels, 9 billion tons per year emissions, instead of staying constant, carbon dioxide is going to keep going up at essentially a constant rate. And by the end of, by 2150, we'll be above 600 parts per million of carbon dioxide. Okay? If instead we decrease by 2% per year around the planet, then we'll actually stabilize and settle down roughly to something that looks like a bit more than 400 parts per million per year. It is almost inconceivable that we will do anything more aggressive than that. This is essentially what's locked into the system. If we actually shut it down now, then the system would relax down to something like 350 parts per million, because a little bit of carbon dioxide goes into the ocean. And I think this is a reasonable place to end up on. There's a whole bunch of other things I would love to talk about, but in the interest of time, I won't. But I do want to extrapolate this out a little bit, because this is, there are 4 things going on here. Basically, well, let's just talk about 2 of them. Of the carbon dioxide that goes into the atmosphere, that we see in the atmosphere in any reasonable amount of time, basically half of it is going to go into the ocean with consequences, ocean acidification, over the time scale of a couple of hundred years. And that's this relaxation that you see. But you see that the CO2 does not get back down to pre-industrial levels. And it doesn't do so, yes, we hear the tinkly bell, we'll be done in a minute. It doesn't do so because the other half takes 100,000 years to make rock in the casting Walker cycle. And by the way, Jim Casting was a PhD student of my father's, so I know a fair bit about the casting Walker cycle as well. So the story is the carbon dioxide is essentially immortal. And in order to deal with that, we cannot freeze CO2 emissions. This is why energy policy talks about decarbonization. We actually have to do it. Everybody has to do it. And we have to drive emissions to zero in decades. So with that, I will stop. Thank you very much.